Example of XOR using a two-layer perceptron, and I'll be using ReLU rectified linear unit as the activation function throughout. ReLU is very simple to understand and easy to work through in some of the easy to work through in examples. That's why I'm also using ReLU here. Now I've already put in all of the numbers here. The first thing which we want to do is to ensure that we have a good understanding between what these numbers mean and the matrices we've been seeing thus far, matrices vectors we've been seeing thus far in the previous convention, right? And we'll then try to confirm if this network is correct for XOR. And we'll be starting with a simple example where x1 and x2 are both 0. And we would expect the XOR to then also then predict y hat equal to 0, right? So let's just confirm that. I'll be using color coding to better represent these matrices which we've been seeing thus far. Okay, we have the following information already. We have the input data, which is a square bracket 0. It is 0, 0. It's a d-dimensional, d equal to 2-dimensional feature in this case. We have the bias for the first layer. So the bias vector for the first layer. Since we have two nodes in the first layer, so thus the bias vector is a 2-dimensional vector, which is 0 and -1, right? You first put in the bias for the first node, and then you put in the bias for the second node in that particular layer. And then let's look at the weight matrix. So if you remember, for the weight matrix, first we put the weights coming into the first node as different columns, right? As the different columns in the first row. So yellow is the first input, is the weight corresponding to the first input coming into node 1 layer 1, and blue is the second input coming into node 1 layer 1, right? And we just put in these numbers, we stack them across the different columns. So thus we can write capital W square bracket 1 as the weight matrix corresponding to the layer number 1 as 1 1 1 1, right? So the second row is corresponding to the weights coming into the second node of layer 1, right? So we have thus far written A, B, and capital W, which is now sufficient for us to compute the vector Z and then the vector A, square bracket 1, both of these quantities square bracket 1, which we can then take forward into the next layer. Okay, so now I'm computing Z square bracket 1, which is the summation corresponding to the first layer. And since we have two nodes, so Z square bracket 1 would be a 2-dimensional vector, and we've already seen the formula. So it's simple. It's capital W square bracket 1 times A square bracket 0 plus B of 1. We have already written these quantities now. So this is basically 1 1 1 1 multiplied by 0 0 plus 0 minus 1 plus the bias which was 0 minus 1. This entire thing evaluates to 0 minus 1, a 2-dimensional vector. Now we can compute the activation. Which is ReLU. If you remember the definition of ReLU, so ReLU is just the max of 0 comma z, and ReLU is applied here element wise. So which basically means you do max of 0 comma 0, which is 0, max of 0 comma minus 1, which is 0. Thus the activation corresponding to the first layer is a vector 0 0, right? Now we'll take this and then again move forward for this particular example. So we've seen that A square bracket 1 is 0 0, which is after applying ReLU, and we can also now write capital W square bracket 2, which is the weight corresponding to layer number 2. Now, since we have only a single node in layer number 2, and we have inputs coming in from 2 nodes from the previous layer, so thus the dimension of capital W square bracket 2 is 1 row and 2 columns, and we just put in those weights. So capital W square bracket 2 is 1 minus 2, and there is only a single bias element since there is a single node in this layer, which is 0. And now I can write z capital z square bracket 2 as the multiplication of w square bracket 2 times a of 1 plus b of 2, which is 0. And if you apply ReLU on top of this, you'll again get 0, which is the desired output, right? So if you remember, we would have expected when both the inputs are 0, XOR should give you a 0. So we've been able to now work through this example, and it seems that this network is correct, at least for this particular example. Now, I leave it up to you as an exercise, and I think it's an important exercise. This will help you clarify the concepts and work through all of the weights yourself, is to confirm if the network is correct for a different example, which is inputs are 0 and 1. I have already done that here, and I've basically shown that this is indeed the correct answer. Okay, so now we come to another interesting thing. So thus far we've been dealing with single examples. Like if you remember, we first verified XOR for 0, 0, then we verified XOR for 0, 1. But that's not how we generally do machine learning. We feed in the trained data, and we feed in the test data, and we get the prediction for that entire. We get the entire array as a prediction. We don't get a single element each time, which means that our procedures are well optimized for dealing with an entire data set worth n examples rather than one example at a time, which is exactly what we'll now try to do. We'll be doing the computation of the forward pass of the neural network for n examples, not just one example. So we're going to write the capital X as a matrix. And before that, let me in fact introduce the convention. So I'm going to write subscript and this circular bracket I to indicate the ith example, or the ith sample number, or the ith instance, right? We know that so we know that each instance is a d-dimensional vector. Thus we can write X subscript circular bracket I to be a d-dimensional vector, or d is also equivalent to n0, right? Because it's the number of neurons in the 0th layer. So thus we can write X to be equal to X subscript 1 transpose as the first row, X subscript 2 X subscript circular bracket 2 transpose as the second row, and so on and so forth. Now this gives us the familiar shape that we are so used to, where the input matrix, as we also use in scikit-learn, input matrix consists of n rows and d features as d columns, right? So thus our input matrix X, which is also written as capital A square bracket 0. So capital A again here means that it's the activation corresponding to, it's a matrix firstly, and it's the activation corresponding to the 0th layer. But since it's for all the n examples, so its shape is n cross n0. n0 is again the number of features, right? So with this in mind, we'll now be trying to repeat what we've been doing previously, but make it work for all the n examples instead of one. So to make this computation easier, we'll see what we have already done. So we have already done that. We have already computed z of square bracket L, and when we computed z of square bracket L, we were doing it for a single example, right? So let's say that we are doing it for the ith example. So we know that z of square bracket L subscript circular bracket I, which means for the ith instance, we can write this as w capital W subscript L, or let's say we're just talking about the first layer. So capital W superscript square bracket 1 multiplied by a 0, a square bracket 0 indicating the input, the ith instance of it, and the transpose of this entire thing just to match up the dimensions, plus the bias vector, which is plus b square bracket 1. And we want this entire thing to be n1 shape, right? So because we wanted it to be n1 shape, that is why we did a transpose over here. And you must have already seen that the w vector and the b vector, the w matrix and the b vector are independent of I, which would make sense because you're trying to learn a set of parameters across all the examples, are not specific to any given example, right? So I'm going to rewrite the entire thing again in a slightly simpler sense. So I'm going to write z square bracket 1 subscript circular bracket 1. So I'm computing the summation term, the summation vector for the ith, for the first layer and for the first example, right? So this is going to be of the dimension of the number of nodes that we have in the first layer in this example, and this we can write as capital W square bracket 1 times small a square bracket 0 and subscript 1. So corresponding, so basically the input features corresponding to the first example plus b square bracket 1, and we repeat the entire thing across the n examples, right? So each of this z is a vector now. If you see the shapes, each of these z is a n1 dimensional vector because this is giving you the summation terms for the entire layer and not just for a single node. And you have done this for n such examples, right? So I've just written this down again, showing the shapes in blue. I can combine this and rewrite this entire thing. So basically now you have n examples or n values of n1 dimensions, right? So you basically now can create an n cross n1 dimensional matrix from this. And since matrix is represented in capital letters, we now write capital Z square bracket 1, indicating the activations corresponding to n examples for layer number 1 as this term, which is basically now just writing each of the individual for each of the individual examples from 1 through capital N. We just take the transpose and put them as different columns in this matrix, capital Z1. So another way to think about this matrix is that eventually once you've computed capital Z of 1, you'll then compute capital A of 1, right? And we're going to stick to the convention that we want these matrices in the format of number of examples as the rows and number of features as the columns. And the number of features here is the number of nodes that we have in this particular layer. So that's one way to think about how we would have come about these shapes. So we can calculate then capital Z of square bracket 1, and this will be of the shape n cross n1, right? Now let's again revise the computations required for n examples. Firstly, we have the input matrix A0, which is of the shape n examples and n0 features, right? So n0 equal to d features. The weight matrix for the first layer, W, capital W square bracket 1, is of the shape n1 cross n0. The bias term for the first layer is equal to the number of, it's a vector equal to the number of nodes in that first layer, which is just n1. And we can also then write this, we can basically repeat the elements in small b square bracket 1 and write this as capital B square bracket 1, which is just writing B1 transpose capital N times, so corresponding to the number of examples. And you'll see why this is useful to do. In Python, even if you don't do this operation, you'll benefit from something known as broadcasting. But I'm just creating this capital B here to make the matrix additions easy, because you want the same dimensionality before adding to matrices. And we've seen that capital Z square bracket 1 is now a n cross n1 dimensional vector, or matrix, sorry. So just writing this entire thing vectorially, because that's again vectorially, and in terms of matrix computation, that's one of the goal of trying to make these computations easy. We can write capital Z square bracket 1, which is n cross n1 matrix that we want. A0, if you see, is n cross n0, right? And W1 is n1 cross n0. So if you do W1 transpose, you'll get n0 cross n1, and that's what effectively we've done. So Z1 is A0, W1 transpose plus B1. So B1 is now n cross n1, Z1 is also n cross n1. So now the dimensions add. So I hope this made sense, and I would again urge you to stop and just verify that all of these dimensions makes sense to you. So based on what we've thus far written, we can now rewrite the general case for the Lth layer. We can write capital Z square bracket L as capital A L minus 1 times WL, capital WL transpose plus capital BL, right? So that's just the generalization of this thing. And then we can compute the activation function on capital ZL, which again is computed element wise. So you compute this on a per element basis in this matrix, right? Let's now repeat the procedure for XOR, but instead of now using one example at a time, we'll use a newly found knowledge and apply it on all the capital N examples in one go. So our input feature is the familiar scikit-learn formatted input matrix of in this case, 4 examples, 2 features. Y hat is 4 examples, 1 feature. Oh, sorry, just the output. It's a vector. Capital W square bracket 1 is what we've seen already. So it's a 1, 1, 1, 1, 2 cross 2 matrix. Small b superscript square bracket 1 is the bias term corresponding to layer 1. That is a vector 0, minus 1. But we then just repeat the elements of this, and we get a capital B square bracket 1 as the bias term corresponding to the n examples for layer number 1, which is again which is now a 4 cross 2 matrix. And if we do the calculations, so we calculate capital Z1 as capital A0 times capital W1 transpose plus B1, which is the multiplication of a 4 cross 2 matrix with a 2 cross 2 matrix. This term will be a 4 cross 2 matrix. plus a 4 cross 2 matrix. So the entire thing is now 4 cross 2 matrix. Right? And once we have done that, we can apply ReLU element wise on capital Z square bracket 1. So ReLU applied on 0 gives us 0, ReLU applied on -1 gives us 0, applied on 1, 0, 1, 0, 2, 1 gives us 1, 0, 1, 0, 2, 1. Right? So you get a 4 cross 2 matrix. Then you have capital W square bracket 2 as 1 comma minus 2 and small b capital 2 as small b square bracket 2 as 0. You repeat it again for the n examples to get a capital B, which is 4 cross 1 vector now. We apply the same things, same procedure again, and we get capital Z square bracket 2 as capital A square bracket 1 multiplied by capital W square bracket 2 transpose plus capital B square bracket 2, so we had already obtained the activation from the previous layer, which is a 4 cross 2 matrix multiplied by a 2 cross 1 matrix to get a 4 cross 1 matrix plus a 4 cross 1 matrix, which is a 4 cross 1 matrix 0, 1, 1, 0. Finally, you apply the ReLU functionality on top of this, and since all of these quantities are non-negative, the output or after the activation you'll get the same thing. So thus y hat is 0, 1, 1, 0, which is the same as the ground truth, which means that our network is doing a good job in identifying the train examples correctly for the XOR case. So we've thus far now seen how to even classify multiple examples in one go using a very simple vectorial calculation scheme of things. Before we discuss about backpropagation and how to learn these parameters, we'll just do one final small thing. And this is to just understand the number of parameters in our models. This is a very useful thing to know. Specifically when you're trying to understand that what is the size of your model, is your model going to be over parameterized, under parameterized, or get a better sense of the memory footprint and the computation footprint. So we have the parameters on a model as capital W square bracket L and small b square bracket L for each of the layers, right? So these are the sort of parameters that we fine tune and we then apply our matrix operations on them to make a prediction. So the question for you is that what is the number of parameters for the XOR example, right? So one way in which you can find the number of parameters for the XOR example is to just go back to the, let's look at this. What are the number of numbers I've added here? That's the number of parameters. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have 9 total parameters. The other way to look at the number of parameters is to just look at the dimensionality of the different matrices and the vectors involved, right? And here I'm presenting a general way in which we can do the same. So firstly, the number of input features, which is n0, is 2. The number of nodes in layer number 1 is n1, which is 2, and the number of nodes in layer number 2, or the output, or the final layer, is 1. The dimensionality of capital W1 is n1 cross n0. So n1 cross n0 is 2 cross 2. So we have 4 parameters. The dimensionality of B1 is the number of neurons or nodes in layer 1. So that is n1, which is 2. So thus we have 4 plus 2, 6 parameters. The dimensionality of W2 will be n2 cross n1, which is a 1 cross 2 matrix. So 2 more parameters. 6 plus 2, 8 parameters. And finally, B2 would be the number of nodes in layer 2, which is just 1, thus 1 more parameter. Thus in total we have 9 parameters. So in general, we can write the number of parameters to be the summation over the number of layers L as NL into N of L minus 1. So NL into NL minus 1 is basically telling you the dimensionality of the W matrix at the nth layer, plus NL is telling us the dimensionality of the bias term, or the number of nodes and the nth layer. So with this, we'll take a pause, and when we'll return, we'll be discussing about how to learn parameters in a neural network. Okay, thank you.